stuff, let's just say. So, excited. Round of applause for Luke.
Yeah, this is me. I am a senior red team engineer at GitHub, where I specialize in macOS malware and TTPs and things like that. I'm also the co-founder of Forian, which is a cybersecurity startup doing endpoint detection and response. And I've done consultancy and other bits and pieces like that before. You can find me on GitHub, Twitter, and all that kind of jazz. A little closer. Okay. So I don't know if Andy and Patrick did this on purpose, but it's super cool because all of the talks have come from completely different security disciplines. So it's kind of a nice insight into what everybody does. I thought I'd do the same and give a bit of a red team 101 on what I do. And I'm going to heavily caveat this with like, nobody can agree what a red team is or what a red team does. And people argue on Twitter about it all the time. And I don't want to incite any more of that. So this is my personal view. But effectively, we hack our employers and the clients, if you're in the consultancy side, to demonstrate security threats in a real world setting. We have tangible goals. So things like steal X million dollars from a bank would be a great goal. And this is because when you've finished this and you've demonstrated all the things that you've done, nothing hits home more than I actually did the thing. Like exactly what attackers are trying to do is what we did, and it leads to things getting fixed. The other side of this is the blue team, whose job it is to protect the organization from all the attackers, but also us who are doing this exact thing. And then crucially, this work is done covertly. So the blue team wouldn't be given a heads up. They probably don't know really what's going on with the kind of red team space. And this is so we can get an honest and realistic view of what the actual susceptibility of the organization is to the type of threats that a red team is emulating or simulating. Effectively, what this boils down to is make somebody's computer do bad things and don't get caught while doing it. And don't get caught while doing it is actually the hard part. It's quite easy to do number one, but now with all of the kind of advancements in the operating system level and all the security tools that sit on top, this is kind of the key part. And most of what my kind of talk is going to be on. So I wanted to introduce a couple of tools that are all open source, so you can go and play with these. So the first one is Mythic, which is an open source C2 framework. C2 is effectively how you orchestrate your implants. So after you've compromised somebody, you need a way to tell the malware to do something, get the results back. That is C2, that is Mythic. That isn't the actual code that is running on your targets. Mythic supports loads of them in loads of different languages. The one that I'm going to talk about today is Medusa, which is a Python implant written by a colleague of mine. So I have a brief video just to kind of set the scene. Yeah, this is visible. So on the left is the attacker box. On the right is the target. This poor unsuspecting victim has downloaded a malicious file, which is a Xcode project. They get a little warning, but everybody clicks through those, so they do as well. We have some lovely little Xcode project written in Swift. And then when they build it, malware gets downloaded, runs in the background, and comes up on our implant framework on the left. From there, you can see I've run a command, ls. All future demos are a bit bigger than this, but I need to show them side by side. And you can see we're getting a bunch of results back. And this is because the box that we've compromised is communicating with us over the internet, and we're issuing those commands. You don't need to really worry about kind of like the specifics of the compromise, but just to kind of set the scene of what we're dealing with. And come on. No. Okay, right. So we've compromised the system. What do we want to do next? We like credentials. Credentials let us do more things. We could look for SSH keys, cookies, passwords. Maybe they've got a passwords.txt file on their desktop. That would be fantastic. We might want to get persistent access. So if they turn their device off, we would lose this. Maybe we want something to start when the system starts, like a launch daemon, to re-get that access back. On the topic of credentials, maybe we want to keylog the user. We could take a screenshot to kind of see what the user's doing, maybe inform our next steps. Or we could perhaps sniff the clipboard to see maybe they're copying passwords around between a password manager. This would be a great way to do that. And this is what we're going to focus on. And the reason we're going to focus on this is a bit of a kind of toy example is because in the latest versions of Python, Python 3, which is really the only version of Python we care about anymore, because that's all that's installed on people's MacBooks, doesn't support sniffing the clipboard in the latest versions of Medusa. And there's a bunch of reasons why this is the case, namely the Python libraries that this relied on no longer ship by default with macOS. So it just doesn't work. So together, we are going to re-implement this functionality back into Medusa and see it all work. So how could you implement something that steals from the clipboard? So kind of, at a kind of level one of this, there is a command called pbcopy, which, it's actually pbpaste, that reads from the pasteboard and outputs it. That's a pretty good start. All the kind of hard work's been done for us. You can see on the right here, run the command, outputs the clipboard buffer, super easy. Why might we not want to do this in practice? Oh, no, jumping ahead of myself. Let me show this working. So this works completely fine. For example, if you run the shell command in Medusa followed by any other command, it just runs that as a sub-process. And the talk we had earlier kind of showed some of this in both the malware setting and the IR setting. We can do a bunch of stuff. And if we run shell pbpaste, it will give us the output of that clipboard buffer, which was a bunch of random words that I copied out of the Xcode project. So this works. This practically works. Oh. It's really hard to move on from these. Okay. However, why might we not want to do this? So, and this is a key part of red teaming, a key part of what I'm thinking about day to day is what impact is that having on the system? Is it going to cause a pop-up? Will the user be alerted? Is it going to be blocked by security tooling? Will it leave logs behind? And this leaving logs behind is a really key part because blue team security products, they use these logs to write rules. Rules detect malicious activity, which in this case is us. We don't want that because we want our malware to stay and do the job that it's designed to do. And the problem with shelling out or like making a sub-process is we get logs for it. So this is a kind of log sample from the ESF framework. You can see that there was process execution. It was pbpaste. Parent is Python, and a bunch of information about where it kind of come from. Like this looks super suspicious. Like why is Python reading the clipboard all the time? And perhaps there could be a rule on that. Gets investigated. Sad, red team, because their malware got detected. Using APIs are way stealthier. So this is Objective-C, and a way of doing this in Objective-C. So we're importing AppKit, which is the kind of UI framework on macOS. We're getting access to the pasteboard, and we're searching the pasteboard for anything that looks like plain text. No sub-process, basically no logs, super hard to detect, which, happy red team. But the problem, we're not in Objective-C, we're in Python. So can we, without dropping a new binary that's Objective-C or anything like that, in still a stealthy way, get access to the information, not produce logs? And that is what I'm going to spend the next 10 slides proving to you. So there's a bunch of people that have already done this, not for the red team case, just for like development normal case. They have written bindings between Python and Objective-C. I didn't opt to use these, and there's a few reasons why. One, they use a lot of C that's compiled to bridge between the two languages. For me, I just want like a clean Python file that just runs. So that was kind of not something I wanted. They were missing a few kind of advanced functionality like blocks. Like Chris talked about blocks a little bit during the decompilation stuff. These don't support that. At least the one on the right doesn't support that. And then the most important reason is I have no idea how this works. And I didn't think I was going to understand how it worked just by looking through hundreds of Python files. I wanted to write it myself. I wanted to kind of gain that knowledge because maybe there's a better way of doing it, a more stealthy way of doing it. And I could kind of just, build that knowledge for myself. And I'm going to bring everybody with us on this. So real quick, we need to take a little look into Objective-C. It's not super deep. And Chris, again, has given you a precursor already on Objective-C, so that's super helpful. But what makes Objective-C different from C? I would say this is the Objective-C runtime. So this is a library that runs inside the process that powers the whole thing. And it allows you to do kind of crazy things. So you don't need to know like methods for a class, compile time. You can call a function on a class, and that class might just be like, no, I don't want to answer that. Go speak to this object instead. And all these things that are powered by the runtime. And this has a few kind of implications for us. And what it really means, and one of the most important parts that we're going to look at, is that the compiler doesn't know where the functions should actually go to. So when you call a function, the compiler has no idea, because it might not actually be there when you actually get to running it. So the runtime is actually deciding when you call a function, which bits of which function pointer it actually gets jumped to, and which code is actually being run. Now, Apple have released all the information on this. You can see all of the C functions that power the runtime. You can load the library and you can call them yourself. You can call them from Objective-C. And really all that's actually happening under the hood when you compile an Objective-C program is it's just calling all of these functions. Again, in the decompilation that Chris showed, you could see all of these things being called, all the message sends, get properties, things like that. And just to prove to you, don't really worry about all of the assembly unless you took the class yesterday. But this is decompilation of a fairly simple Objective-C application. You can just see that the compiler is just calling these runtime functions: Objective-C auto-release, pool push, Objective-C alloc, Objective-C message send. It's just stringing these together to power the application, which is neat because we can effectively do the exact same thing. But just being able to call them isn't completely useful. We need to know effectively what order to call them to be able to achieve functionality like Objective-C does. So we need to know a little bit about message sending. You could say function calls, but the more true concept is message sending. And to kind of explain the notation here, if you look at the myString length, you are sending a message called length to the myString object. If you look at the example down here, the same thing. You're sending the message general pasteboard to the object or class in this case, which is kind of the same thing at this point, NS pasteboard. And this is kind of how function calling is implemented on Objective-C, because it's the runtime that's making the decision. I'm going to really labor this point so when we start doing this in other languages, we're all here. So how does this work? What are we sending? We're sending the message, also known as a selector, which is pretty much the function name. It's like string for type, colon being where an argument would go, and any arguments. That's the message we're sending. Where are we sending it? We're sending it to the receiver, which is the object that will receive the message and decide whether it wants to execute that code. How are we sending it? The Objective-C message send function. It's a runtime function. It's exported by that library that I was talking about. You can just call this and implement this yourself if you want, which foreshadowing is exactly what we're going to do. We can look up the function in the runtime docs. And again, what are we sending? It's the selector, the function name, and any arguments. Where are we sending it? The receiver, which is the object that is going to receive the message. And then the message send function is how we're doing it. As a first step, I wrote this in Objective-C, just interfacing with the runtime itself, which is, again, a cool thing you can do with Objective-C. So again, I'm really laboring this. What are we sending? We're sending the selector and any arguments using the message send function, and we're sending it to the receiver, which is the object that's going to pick it up and decide whether it wants to execute that code. Okay. I'll take one step back slightly. So what this effectively allows us to do is to use a C-based library to make Objective-C runtime function calls, which is equivalent to just making Objective-C calls. And this is great because Objective-C has all of these nice APIs that we want to use, things like reading from the clipboard, taking screenshots, all that kind of stuff. But again, we're not in C, we're in Python. So there's one more piece here where we need to go from C to Python. This thankfully has been done time and time again, is a very popular and default Python library called C-types. C-types lets you load a library and make C calls, and that's all it does. So it handles a lot of the typing for you, but effectively, if I kind of step through this, line 4, it's loading the library. Line 7 and 8, it's setting the types. Line 11, it calls it. Kind of straightforward in its implementation. It's obviously doing absolute magic under the hood, but we don't care about that. It's just calling the functions. Okay, so that's the missing piece of the puzzle. So we can now get from Python to Objective-C by kind of working through these steps. So Python loads C-types, C-types loads the library. We call methods in the library using the message send function to interact with the runtime. You don't need to really, don't really worry about understanding all of the code. I just want to make the point of this is now Python. This is C-types because we're loading the library. And this looks super similar, right? Because we are calling the message send function with the thing that's going to receive the message and then the message itself, which kind of brings this back all together. Oh, I've lost a bit. So how do you make this usable? That's quite a lot of code, especially when you bring back in the argument stuff that I took out for time's sake, to make one function call. And in that case, all that did was allocate memory for a string. It didn't even give it a value. So we need to abstract all of this away, wrap it in a nice interface, and kind of make it usable. So I stole the interface from all the libraries that are already doing this in hundreds of Python files that are doing it well. And now it looks something like this. So shortcuts for loading the libraries. You have a base object with anything that you want to allocate or get a reference to, and then you just call functions on it like you would Python. And under the hood, it's doing all of this translation from Python into Objective-C. Taking a way step back, why are we even doing all of this? Well, what we're trying to do is steal the password from this box as it gets put into the clipboard buffer. So if I compare these two kind of code snippets, this is the original Objective-C that I presented with Stealthy. And then this is the Python translated using this layer that we've built, which does the same thing. So hopefully you can kind of see the similarities. Import AppKit, load library AppKit. We're getting the general pasteboard from pasteboard. We're getting the general pasteboard from pasteboard, setting our string types and getting the output. And this is no sub-processes, basically no logs, because it's all done in the same process. What does this look like back in Mythic? So we add the code to our implant. I can grab a process listing, see what's going on the box. So this is everything that's running. I'm looking for things like Chrome. I'm looking for things like password managers to get an idea of what type of thing I want to run. I can see Chrome. I can see a password manager. That's pretty sweet. I'll grab the clipboard and see what I can get. It's running the code that we've just presented under the hood and then pulls out the password. We don't just have to use this for the clipboard. Any native APIs can be used by this in the same stealthy way. So, for example, the exact same thing can be used to take a screenshot. I'm going to fast forward this while it sends 37 chunks of screenshot. 37. So the malware's running, it's taken the screenshot, it sent it back to my C2 platform, and then I can see the screenshot that I took of our target. So this can be used for literally anything that Objective-C can do now, but in a way stealthier way. So keylogging, persistence, bridging to another language. Objective-C can load other languages in. So maybe you want to go Python, C, Objective-C, JavaScript, just to really annoy anybody that's trying to reverse engineer your malware. And that's effectively the premise of this, is that shelling out, not so good, generates logs. If you can keep it in the same process, you're already winning from a malware development standpoint. And the bridging into C and Objective-C makes that quite nice. Um, conclusions. So this isn't a contrived example. This was like actually something I had to do. I wanted to read the clipboard from a Python 3 process and I couldn't do it. So I worked out and did this. So if this kind of stuff is interesting to you, then maybe red teaming is a good place for you to go. I'm going to release this open source in a couple of weeks. So if you want to actually look at the code, you're absolutely welcome to, and criticize my slightly bad Python. And then I think the most important point is you learn way more from doing this stuff yourself. Like I could have just looked at these libraries and tried to load them, not really understood what was going on, and kind of gone that route. But ultimately, this process is what allowed me to really understand how this stuff works under the hood. And I highly recommend you to do the same. So when I was starting out, I would see a blog post that somebody had written, and then I would try and replicate the exact thing that they've done. And it's easy because you've got the blog post, so you can just see what they've done. And yeah, makes it a lot easier. And then lastly, on the kind of like the macOS point is like system APIs are basically impossible to get logs for. The less visibility defenders have, the less burnt shells we have as a red team, which makes us happy. A couple of tool shout outs. Mythic is absolutely awesome, as is Cody. If you want to play with this stuff, obviously only compromised computers that you are allowed to do so. Super good. Python implant written by Alfie is super easy to understand because it's all in Python. I use Hopper, not Binary Ninja. Sorry, Chris. But Binary Ninja looked pretty good. I just don't have the license. So, and then last thing I really wanted to show was this blog post about getting started in macOS security, which just has a ton of links to blogs, courses. It's a couple of years old at this point, but it's still super good. So I'll put the link back on in a second. But if you are looking for more stuff like this or any of the talks today, this is a great place to start. Now I'll just whack that old link back there for a second.